Come on, guys. Some claps, please. All right. There we go. There we go. We gotta wake you up. Okay. So today we'll be talking about how NFL is using Gen AI to streamline research and content creation and discovery. And a very quick agenda. We're gonna give you a teaser to start off, where Eric is gonna demo you how the solution looks like right now. And then we're gonna retrace the steps back to how this project morphed from idea to reality. We'll walk you through the whole journey. Where was the motivation? What's the incentive for us to do this project? How we built an MVP first, and how we took it from the MVP stage to production, and finally wrap it up with the impact and some of the future work we're thinking of. We hope you are very excited about this. Now, without further ado, I'd like to pass it to Eric to introduce the NFL media team and give us a demo. Round of applause, guys.
Thanks, Henry. Really excited to be here today to share our project with you guys. But before I do that, just a little bit about NFL Media at a glance. So we're based in Los Angeles, and we've been around since 2003, starting with NFL Network. That has since grown to include the platforms that you know and love today, Red Zone, NFL Plus, NFL.com, and so on. We've had a long-standing partnership with AWS to develop next-gen stats, and so we looked at this project as a way that we could further what we're doing with next-gen stats to help our content creators to find footage faster for editing together the packages that you guys see on all of our platforms every day. So I'm going to start with a quick teaser here of what exactly our Play Search chatbot is able to do. We've named this Playbook Pro. This is in use by all of our content creators and all of our production team to ultimately find any play-based footage that they're looking for. So if we play through this demo, the user's going to log in. They then have a very similar interface to what they're used to with ChatGPT. You can see that I'm asking the question of Patrick Mahomes' completions, where the completion probability was under 50%. Now, because this does take a little bit of time, it usually takes about 30 seconds to get a response back, you can see that every step along the way, we're using a WebSocket API to actually tell you, as the user, what step of the process we're on. So once it starts generating a response, you get a summary of the plays that you're going to get. You then get a complete list of all the plays that meet that criteria. What you're seeing now is the loading of links that go directly to video that's accessible by within the Next Gen Stats API. This is the All-22 angle, which you guys might notice is an angle that's commonly used by analysts to break down plays during our shows. We also have the Media Portal button. That takes us directly into our asset management system. And from there, our content creators and production team are able to look at any video asset that we have of that specific play. So all of these clips that you see listed are one specific play. They can then, if they choose a shot from that list of plays, they can then go on to the next play. They can, again, preview. This is a different angle that's available within the Next Gen Stats API from the end zone. And if they decide that this is something that they are interested in, again, they're going back into Media Portal. And in this case, there's only one clip that's available, but this is what's called a melt clip. So ultimately, this clip has every angle from the broadcast of the game that's available. So the editor can then go through and determine what it is that they're looking for. So ultimately, if you think about this, they're not just doing this once or twice. They're putting together packages, so they're ultimately going in and out of media portal to find the shots that they want, and then they're taking that into Premiere Pro in order to do their edit. So in the second example, you can see that it's a Josh Allen question. Now, you guys may or may not know Josh Allen. There are 2 of them within the league. So at this point, you're able to be conversational with the chatbot. So it's going to ask you which Josh Allen you're actually looking to ask the question about. You then tell it that you're looking for the Buffalo quarterback. It's then going to go back through that same process, and it's going to give you the summary, and it will then also give you that list of plays again. And the thing that I didn't point out the first time that we went through this is that not only do you get the list of plays, but you can open up for more info. So you can see the exact Next-Gen Stats API call that was formulated by the LLM. And you can also see the reasoning that it used to determine what that API call should be. So ultimately, why did we do this? We work in a very fast-paced live production environment, and lots of times that is not conducive to a long period of time to do searches and bounce in and out of applications. So we've had some great internal Next-Gen Stats tools for years, but those tools generally take a lot of time. You're clicking a bunch of filters. You have to know where all those filters are. You then get a list of plays, but that's as far as it takes you. So once you have that list of plays, you're then doing a specific lookup for each of those plays within the asset management system. So for example, if I had a question where the response that I got was 20 plays, it might take me 10 minutes or more to ultimately pull up all of the video clips by searching within our asset management system. So ultimately, how can we do this in a way that's faster and allows our content creators to search for this stuff quicker and ultimately iterate this so that they can get things back as quickly as possible? So we turned to Gen AI and we said, well, what if we could just let the users ask the question? You know, what if I'm looking for Tom Brady touchdowns on 3rd down in the 4th quarter? And then we let the LLM actually turn that natural language query into a Next-Gen Stats API call. Ultimately, this would reduce the barrier to entry for our end users. They don't have to necessarily spend that same amount of time within the filtered search. They also don't have to know where all the filters exist. And then ultimately being able to turn that into a conversation where they can refine what they're doing. So we turned to Henry and his team at the AWS Gen AI Innovation Center, and I'll turn it over to him to take you through the first steps of our POC.
So as Eric mentioned, AWS and NFL has long-standing relationships and have collaborated on multiple machine learning projects in the past. However, this Gen AI-based project just marks another milestone for this deepened collaboration. So when the team came to our team, the Gen AI Innovation Center, since it's so new for all of us, we decided to take a systematic approach to thinking about what is the right problem to solve. So first of all, we hopped on a couple diagnostic calls where we aligned with the stakeholders and the leadership team from NFL, trying to ask, what are the business problems you're trying to solve? What are some of the candidates that we think might be good to be solving using generative AI? Then we set up follow-up sessions. These are deeper dive sessions where it spans across several hours, where we iterate through each candidate problem. We think through and deep dive to say, what are the exact business use case we're trying to solve, the challenge we face right now in the existing process, what's the data availability, what is the end-to-end user experience going to be looking like, et cetera. Then we really narrow down to one specific use case. that we want to be prioritizing for. After we identify this top priority use case, we jump into this execution phase, where it's a multi-week effort, hands on the keyboard, where we build this proof of concept, or POC, to validate this is indeed the problem we're trying to tackle, and the existing technology is mature enough to solve the problem. So as Eric mentioned, there are many tools that exist in NFL team, which requires different levels of familiarities for the analysts and the researchers to find the content they're looking for, right? And the business objective really is, how can we make that experience easier and faster? Natural language seems to be the uniform and unified language that everybody speaks about. And wouldn't it be nice if we can just find the right content with the natural language query, right? So that's what we set out to do. But there are a couple challenges associated with it. Now, the very first thing is, how can we translate these natural language queries? For example, find me all the plays where Patrick Mahomes throws a touchdown with more than 10 yards this season. Any Chiefs fan in the audience? Okay, great. Like the enthusiasm. So how do we translate this user request into a request or a programming language that the underlying database can understand, right? While there are many tools that exist out there, they're all pinning down the same source of truth, database. So our goal is really to translate this natural language to the database understandable language. But not only that, we need to do it accurately so that we gain the trust from the users that they can reliably type in any kind of queries, and the solution will be able to handle them, as well as efficiently. You don't want to be waiting there after typing a query for 5 minutes, right? You want them to be in a couple seconds that can return you those solutions. So those are the things that we need to be keeping in mind of when we are building these proof of concept. So let's look at this fairly easy query again together. Patrick Mahomes throws a touchdown with more than 10 yards. And let's try to break down this sentence. So the very first thing is you have an entity associated with this query. It could be a player, it could be a team, it could be multiple players or teams. There is an action, throws a touchdown, right? There's multiple actions out there that are very relevant that the NFL analysts and researchers will query on a daily basis. And then there is a constraint, more than 10 yards. And sometimes when people ask these queries, there will be multiple constraints, actions, and entities involved. Also, it is related to an offense scheme. There are multiple database systems in the background where each one is designed for different schemes, such as offense, defense, team offense, team defense, rushing, passing, etc. So the solution really needs to understand which schema it needs to ping under the hood. And the underneath database system, we're using OpenSearch. So it's really relating those couple of elements of the sentence into this set of filters. For example, who is a passer, right? The passer ID associated with the entity. The pass touchdown, that is representing the action, and the pass yards greater or equal to 10 represents a constraint. So let's break down this problem into several pieces. The very first thing we need to solve is how can we identify the relevant entities, right? So we need to find the associating IDs with either the player or the teams. We need to be able to find from this query who is the party of interest that we need to be looking up for. And you can apply natural language processing techniques, both traditional or the Gen AI techniques to do that, right? Now, there are some nuances associated with it when we started diving deep into this problem. The very first thing we learned is that users may only search through last names, which is a very common habit of how people search or ask questions, especially when you allow them to do natural language searching, right? They can use acronyms, and sometimes you can control, but there is typos potentially involved. As Eric mentioned, there are players that have duplicated names. It's even more frequent if they share the same last name. So how can we make sure that the right players are being identified? So what we ended up building is a custom solution that leverages both traditional natural language processing techniques for entity recognition, as well as using efficient large language model to try to map the entities existing in the query to the data in the database and try to see who is potentially involved in this query. And then if a duplicated name is found in the system, we will prompt the user again to make a selection so that the system knows exactly who they're asking for. The next part is identify the relevant actions and constraints. And the goal of this is really to associate these actions and constraints to the correct API filters that we will be using to generate the API query. But large language models off the shelf wouldn't understand all the underlying logic or the rules how to associate these recognized actions to the API fields, right? And we can all associate, but when somebody says something really complicated to you, you can take something for mistake, you can be confused about it, etc. The same applies to large language models. If a user's query is super complicated with multiple entities, constraints, and actions involved, the language model will have a hard time really to come up with all the correct filters that need to be applied to be executed. So we took several steps to address these issues. The very first thing is we did some pre-processing on the underlying, you can say, rules per se, or the underlying mapping logic between the model and the documentations. So we make sure that all the schemas are well formatted to be ingested into large language models. And we're making sure all the dictionaries for each filters, the definition of them, examples of them are clearly included in there so that large language model can have the best knowledge about how to associate these entities and actions and constraints with the API filters. And next, we find that ask models to think step by step really helps. And on two fronts. The very first thing is the model is able to think through all the things that they are seeing in the query and being able to reason about why certain filters are being chosen for them to eventually create the API call. And the second benefit is that we find later on by surfacing this reasoning step to the user, it actually significantly boosted the user's confidence because now they can know why the language model come up with the API call as such, and they can see whether the reasoning behind it maps with their own intuitions. So they can quickly validate and give us feedbacks and help us to make further corrections to the LM behavior. Last but not least, we included both correct and incorrect demonstration to the model to further instruct their behaviors. So by passing the correct information as well as the reasoning steps, the model knows, okay, these are the kind of steps I should be taking when I see these queries. And by passing the incorrect examples, we can help the model to avoid common pitfalls that we are seeing commonly happening during the development. After we set up the pipeline, we start looking at the performance evaluation. right? As mentioned earlier, this is critical because we want to measure the accuracy and efficiency of the solution so that we know it's going to be a nice user experience for the end user. However, when we embarked on the project, there is lack of ground truth data, which makes it really hard for us to evaluate. Now, thanks to Eric and team from the NFL side, we were able to identify domain experts that actually came up with a lot of questions for us for varying difficulty levels, from easy to medium to difficult. So this allows us both to do quantitative evaluations, but also to have a better sense around the capabilities of the model, whether the model do better on easy questions, and do they struggle with difficult questions. We want to make sure that these performance are actually matching up with our intuitions as well. And then the other thing we found really beneficial during the development of this proof of concept is very quick iterations. By 3 or 4 weeks into it, we decide that we want to surface this intuitive user interface so that the end user can start playing around with it. And they can tell us what kind of behavior they're seeing. And they can quickly let us, the GenAI Innovation Center, know, okay, how does this model behavior, where is it struggling? What edge cases is this missing? So that we know how to better prompt the model, how to include better examples and more representative examples, and make the solution more generalizable. So by the end of the POC, we're able to achieve 90% accuracy on the UAT test set, which the model has not seen before. And then the average response time is about 20 seconds for any query. So this is very exciting. It validated that this seems to be the right direction we're taking. However, many of you may know, there's always this huge abyss you need to run from something that's proof of concept to production level, right? And say applies for this project. There are other challenges and consideration we need to take into account when we are putting this into production. For example, how can we provide a more seamless conversational experience, like what Eric showed earlier? User can ask follow-up questions or different questions throughout the same session, right? How can we link the extracted play information with the media assets? Can language model actually leverage user feedback for enhanced performance? And how can we further reduce the model hallucinations by making it to do better, not just 90%, but 95%, or really 99% on the test set, so that user can use them reliably, right? So next, I'd like to pass the stage to Ross to talk about how we take it to production.
Thanks, everyone. All right, so we heard Eric talk about the challenge that was faced at the NFL, and we heard Henry walk us through how we can leverage generative AI to solve this problem. It next falls to the AWS professional services team to take this proof of concept and turn it into a production application that's running within the NFL. And the way we can go about this is by building a system that mimics human decision-making. Ultimately, what we need to do is we need to take a user's request and we need to automate a process that they had been doing themselves. And so we can follow the same sort of guidelines that you might when you're solving this problem yourself. So we want to take advantage of memories. We want to leverage existing memories, and we want to create new memories of what we've done in the past. We want to take a larger problem, and we want to break it down into smaller sub-problems, more manageable problems. And we want to eventually reach a conclusion through the logical progression of these outcomes. And so what we're talking about in technical terms is an agentic workflow. An agentic workflow is nothing but a graph-based architecture that consists of nodes, edges, and state. A node is any action that needs to occur, a function. It's just a function. It could be a language model call. It could be a query to a database, any action that needs to occur. An edge is the relationship between these nodes, and the state is what's being passed from one node to the next. Now, when we put all this together, it becomes an architecture that represents our agentic workflow. What we see here on the screen is an image of what this pattern looks like for this specific problem at the NFL. And so what I'd like to do is walk through each of these steps in a little bit more detail and just talk through what is actually happening and how do we go about this. So we start at the top. Try that again. Here we go. So just like if you were solving this problem yourself, the first thing that we want to do is we want to assess the intent. We want to confirm the user's intent. What am I being asked to do? And this has a couple of benefits of doing this right up top. The first is that it enables a turn of conversation. So if we get requested, find all the touchdowns Brock Purdy has thrown against the Cardinals, we go through, we run the process successfully, we return the results, and then the user asks a follow-up, how about just in the fourth quarter? We need to be able to combine these two requests into a single intent. And we can do that with a language model call right up top. What is the user asking me to do? The other reason it's helpful to do this up top is because it enables us to deflect irrelevant asks. So if someone asks a question that's not related to searching for plays at the NFL, we can say, sorry, that's not what I'm designed to do, let's talk about football. And what that prevents is us running a bunch of downstream compute for a request that's not related to what we're trying to do. Once we've confirmed the user's intent, the next thing that we need to do is we need to collect the entities, right? This is the players and the teams. Who are the players and the teams that are being referenced? And this is that solution that Henry had described where we're doing some matching to identify the team names and the player names. And we want to do this up front as well because, as Eric had mentioned, sometimes we can get duplicate player names. And if we identify duplicate player names, we want to be able to address that quickly before we execute any of our downstream workflow. So we can take those player names and we can pass it to a language model. And we can say, language model, here's what you're being asked to do. Here are the potential players. Can you assert who we're talking about? And if not, we can go ahead and we can kick it back to the user. And we can say, hey, user, sorry, there are multiple players that meet this criteria. Can you please confirm who you're referring to? And again, this enables us to skip the downstream compute until we know exactly what it is that we're being asked to do. So we have confirmed the intent. We have confirmed the entities, the players, and the teams. The next thing that we need to do is just like if we were being asked to do this as a person, what you would want to do is you want to jog your memory and you would want to think, what have I done in the past that is similar to what I'm being asked to do now? And we can implement this in our agentic workflow with a semantic search against a vector database. So we can search our past executions and say, what if I executed in the past that's similar to this request? And we can return a number of things. We can return the task that's most similar. We can return the API call that was used to retrieve that information. We can retrieve the thought process that the language model generated in creating that API call. And we can also return a distance. So when we do a semantic search, it's really just a cosine distance between your search embedding and the nearest embedding in the vector database. And if that distance is small, it means you have a very semantically similar request. If that distance is large, it means it's not very semantically similar. So again, just like if we were thinking about solving this problem ourselves, if we rack our memory and we can't think of something that we've done that's very close to what we're being asked to do now, then we might want to think about that a little bit harder. And the way that we can go about this in this agentic workflow is, as Henry had mentioned, we can go in and we can retrieve documentation for the API. So we can make a language model call and we can say, here's what you're being asked to do. Here are the potential API documentation that you can review. What would you like to review in order to make this API call? And so the language model might come back and it might say, okay, I'd like to review passing plays and general offensive information. We can go collect that documentation for the API, return it to the language model, and make yet another call and say, here's what we're being asked to do. Here's relevant documentation from the API for this task. Use this information to formulate an API call to collect this information. Once we formulated the API call, now we can actually make the request. So this is where we're actually sending the request to the next-gen stats backend system to return the information. In the event that this API call fails, we can introduce error handling. So we can make it self-correcting. We can go back to our formulate language model call and we can say, you just tried to generate an API call for this information. It failed. Here's the error. Try again. And we can introduce a self-correction loop here. In the event that it fails again on the second time, well, we can make the API call yet again. In the event that it fails again, we can kick it back to the user. And we can say, sorry, this is the API call I've tried to execute. This is the error that it's reaching. Can you help provide some clarification? In the event that the API call succeeds, what that means is that we've successfully found the plays within the next-gen stats system that match the very specific search criteria that we're looking for. What we need to do next is we need to take that play information and make an additional query back to the media asset management system, and that's where we can return all of the wealth of media resources that the NFL has that are related to these plays. Finally, we can summarize. And this is where we saw in the demo at the very end. It's going to say, hey, this happened 7 times. Here are some key highlights. Here's a table that has all the metadata associated with these plays, and these are links to the media asset management for each of them. So this is the work, the process flow in the event that the task is unknown. We don't have a similar enough match in our vector database. What if you think about the problem and you remember something that you've done that is quite similar to what you're being asked to do now? So we have a small distance between our search vector and the nearest match in our vector database. It's a very semantically similar match. In this scenario, just like a person, we don't have to think about it quite as hard. We don't have to review the documentation. So we can just go straight to the language model and say, language model, here's an API call that you made for a very similar task. Here's what you're being asked to do now. Just modify the existing API call so that it meets our new expectation. So maybe this is a new player ID. Maybe this is a new down and distance. Maybe there's something minor about the API call, but it already knows how to do it, right? So we don't have to go back and review the documentation. Similar here, we can go ahead and make the API call and carry on about the process. So what this means is that we can enable the system to learn just by using it, right? So without touching any model weights, we can introduce knowledge into the system by enabling it to learn from successful executions and then retrieve at inference time to search for what have I done in the past that's similar to what I'm being asked to do now. So we've talked about how we can do the retrieval. What we haven't yet showed you is how we can actually commit to memory. The way we introduce this at the NFL is we introduce the concept of an admin within the UI. So if I'm an admin, what I can do is I can review the past search history over X amount of time, and I can review it and I can approve it. So in this specific example, we have a user has sent the request, Justin Jefferson receptions in the 4th quarter when his team is trailing. The process completed successfully, we have a summary. What happens next is the admin user can come in to the memory section and they can query for the past executions over X amount of time. And you'll see that this Justin Jefferson should be the very first one, it's the most recent one. And what they can do is they can review what was the API call that was used to retrieve this information. What was the reasoning, what was the thought process that the language model generated as to why they constructed that API call? And if the admin approves it, then they can save. And what that means when they save is they're actually going to write this task along with the metadata back to our vector database. And so what happens is we can start a new session and we can ask a semantically similar question. So in this case, it's Deebo Samuel receptions in the 4th quarter when the 49ers are trailing. Not exactly the same, but semantically similar, effectively the same question. And what you'll notice now is that we're going to go through the modifying path, modifying the existing API. And what this means is that we've gone the known task route. We've taught the system how to complete this, and so it doesn't have to think about it as hard. And what this means is just by using and allowing the system to learn, we can make the whole process faster and cheaper and more reliable over time because the space of the unknown tasks becomes smaller and smaller as we use it. So next up, we can't have a reInvent talk without an architecture diagram. What does the architecture look like? It's probably simpler than you might think. So there's 3 primary kind of conceptual components that are required to develop something like this. The first are language models, easy enough. Next is we need a workflow orchestration. So this is that graph that we had talked about. This is the conceptual components of how we want to organize this architecture. And then the third is memory. So within AWS, if we look at our infrastructure, we can run the workflow orchestration on compute, serverless compute with Lambda. We can take advantage of MemoryDB for Redis for the memory component. And this is a really useful tool because MemoryDB handles not only the short-term memory, the session state, the conversation history effectively, but it also enables us to use semantic search so we can use the long-term memory. So one memory store, 2 types of memory. It simplifies the architecture. We have Bedrock for the language model calls, and as Eric mentioned, we're leveraging WebSockets API for the streaming of not only at the tokens at the very end of the workflow, but also just the process updates. So as we're making our way through the graph, we can post back to the user and we can say, now I'm generating the API call, now I'm searching for relevant teams, whatever it may be, we can post this back to the user to improve that experience so they're not just staring at an empty screen and waiting for the response to come back and improve the experience. And the beauty of this architecture is that it doesn't much matter what that agentic workflow on the back end is. We still have these same primary components. We still need memory, we still need workflow orchestration, we still need language models. And it's up to you as the developer to build that back end, that agentic application on the back. And so what that means is that there's plenty of opportunity for enhancements and improvements and new use cases. And so with that, I'd like to ask Eric to come back and Henry as well. And so we can talk about how the NFL is thinking about taking this further. What other use cases might we implement?
Thanks, Ross. So just to talk quickly about sort of the keys to success for this project. You know, we were ultimately able to get to an MVP very quickly and get this into the hand of some alpha testers, people that, you know, could push on the system in various ways. We could start to find the edge cases, and we could continue to develop off of that. And then once we got to a point where we felt comfortable, actually getting this into the hand of some beta testers, of actual end users, because I think what we found is the end users are asking, in some cases, very different questions than what we would have expected. In some cases, maybe not quite understanding the edges of what they can ask. So there was some user education as well. But generally speaking, it allowed us to find these edge cases where we could continue to refine and make a better product. And ultimately, we did this very, very quickly while we were still involved, first in the original POC and then in the PRO301 engagement, so that in both cases, we were able to continue to iterate quickly and make improvements, get it back into the hands of the users to continue testing. So ultimately, the impact of Playbook Pro has been pretty incredible. We got it into production in August, just before the season started, and within the first month, we had onboarded about 250 users to be able to log in and use this in their day-to-day work. So where before I was saying, on an example where you might get 20 plays as your response, that originally would have taken about 10 minutes in the old way using just those filtered searches. We've now taken that down to about 30 seconds. And after those 30 seconds are up, you can quickly bounce in and out of your asset management system to find all of those clips that you're looking for. Ultimately, this means that it gives our end users, the content creators, more time for actually reviewing the footage options that they have available to them. And this lets the content creators spend more time in the creative space and less time in the details of how to get to that point. So obviously, we started thinking about, you know, what would the next steps be for continuing to make improvements. I think ultimately, you know, we're currently using just a single next-gen stats endpoint. We chose that endpoint based on, as Henry mentioned, it's based on an OpenSearch database. So the response time is very, very fast, but we're limiting the scope of the stats that are available to us. So by widening this out in a future phase so that we can include more of the next-gen stats API endpoints, we can expand out the sorts of stats that we can query. In addition to that, we also have what's called the NFL API. That would allow us to start to ask questions like biographical information. You know, where was Patrick Mahomes born? You know, what year did Tom Brady retire? Things like that. Also, this solution only covers players that played in the next-gen stats era. So Next-gen stats has only been around and we only have access to stats within the database we're currently querying back to 2017. So how do we expand this out to include questions about Jerry Rice, questions about Terry Bradshaw, things like that? And then ultimately, how do we make this into a fan-facing application? These are all things that we're thinking about. Lots of places that we can go in the future with this, but that is for another time. So thank you. If you want to connect with us on LinkedIn, you can. Please fill out the survey, and we're all ready to take questions if anybody has any.